Good morning, everybody. So we had quite an open slate as to where we could take this talk, but we really wanted to keep it light, and so we have Saturday morning physics light now with 40% less facts. We know it's not grammatical, but you know, we're trying to have fun here. So before we get started, I just wanted to kind of give you an idea of what the demo lab does, how long we've been around, and then get into the fun of today. So as Tim Shep said, the official capacity of the demo lab started in 1986 when Warren Smith was hired by, in February, and by the end of the year, he was already a full-time staff member. And to give you an idea, we have so much business that we have 3 full-time staff members working constantly to keep up with the requests. We have over 1,000 unique demonstrations that can be applied in multiple areas of physics, so it kind of increases our catalog to a little bit over 1,100 if you were to count all the different variations of a single demo. We also have 45 student labs that are geared towards non-physics majors, so these are more simple, direct, everyday, hands-on kind of things that these people who have no real interest in science can actually do some real cool stuff. And it's really accessible, and we also gear this towards our elementary school teacher physics class to, again, give them ideas to help broaden the scope of our reach. So again, what do? We provide physics apparatus to lecturing professors to help give real-world examples of what they're trying to talk about in class. Because, you know, although math is really pretty and it tells us a lot, sometimes it's nice to actually see that in action. And so that's what we do. The pictures here are our work area. The one on top is our storage area. And you can see there's many rows that we have cataloged in order to keep track of all of those demos, as well as our work stage area, which is the second picture. And you'll see that there's a staging in front of the TV that's in the center of that. And on either side, you'll see that we have a shop. I didn't get a lot of pictures, but you get the idea. So we also work with student groups for outreach activities. Some of those include Society of Physics students, Wise Guys, Physics Olympiad. Again, we try to provide demonstrations to reach more people and get them excited, again, about physics and science in general. And then our favorite thing is to actually put on the demo shows ourselves. We do get the opportunity beyond just something like this. We get to work with K-12 classes. They may come in for a supplementary activity, as well as seminar classes, and we have even been added to some of the enticing group tours to try to get people to come to the University of Michigan, because we are special in the amount of demonstrations that we do have. All right, so to begin the demo show, we wanted to each talk about an experience we had with a demonstration that really intrigued us, that may have been a little surprising at first, or something that was really memorable that kept us going. And so to begin with that, I have a story about 6th grade science class. So my teacher, Mrs. Worthington, came out in front of the class and she said, "I can take a bucket full of water upside down over my head and not get wet." Of course, everybody was like, "Well, okay, well, let's see it. We've never seen that, come on." And sure enough, she swings it over her head and does not get wet. And so, you know, she didn't go into detail about how she was gonna do it, but it opened the door to be able to explain what was happening. And so my arm is attached a rigid length to the bucket. It provides a center-seeking force that keeps the bucket going around in the circle. Now the water inside the bucket has some velocity. It wants to continue going in a straight line just like Newton's law says. But unfortunately, the bucket gets in the way. And so the bucket ends up pulling the water around in a circle. Now as long as you go fast enough that the water is moving faster than gravity, you have no issue. But, you know, as my teacher is explaining this in front of the class, little Timmy raises his hand and he says, "Oh, Mrs. Worthington, what happens when you stop?" And sure enough, you never forget it. All right. And mind you, she did do that in third hour, so I feel her pain.
All right, is this thing on? Is it working? Good. So something that was, we'll say, intriguing to me, mostly because I got it wrong. And so the question is, if I make two bubbles of different sizes and connect them together, what's going to happen? Well, let's just do it. Okay. So while this is starting, make a prediction about what you think is going to happen, and we'll see later if you were right. Oh, lovely. There we go. All right, can you see the bubbles now? Okay. All right. So while this is going, it takes a few minutes. I had thought that the bigger bubble has more air in it, which means more air pressure. The little bubble has less air pressure. And so that high pressure on one side should push air through the straw to the other side. Right? But that's not what happens. I can't see again. There it is. All right. But what happened instead was the little bubble disappears and the big one gets larger. As it turns out, the surface tension on the bubble means that the pressure inside is actually proportional to the inverse of the radius. So the bigger the bubble, the lower the pressure. The smaller the bubble, the bigger the pressure, which drives air the other way. Now, quick show of hands, who got this wrong? Yeah, it drove me nuts until I figured it out, and then I kind of like it now. All right, and so that's one that stuck with me. I hate getting things wrong. All right.
Okay, let's just test. Okay, and for me, gyroscopes were my favorite demonstrations to learn about. In particular, the ones that were performed by Eric Laithwaite at the Royal Society of London back in the 70s. Eric Laithwaite was a professor of electrical engineering at the Imperial College of London. He's famous for inventing the linear induction motor, which is used heavily in magnetic levitation applications and is considered the father of maglev. His success, however, is often eclipsed by the claims that he made that spinning objects weren't fully understood yet, and that in some references they could lose weight or transfer their weight somewhere else. This got him labeled a heretic in his older years, and the claims were considered on par with anti-gravity or reverse-engineered spacecrafts. Okay, but I'm going to show you 3 of my favorite demos that he also performed, so you can decide for yourself whether they are fully understood or not. Okay, so here I have, for the first demonstration, just an average bicycle wheel, which is attached to a long rope. And now when I let go, it just simply wants to hang down and gravity wins. So let's see what happens when we spin it up. So now that we've given it a spin, and we perform the same action, and I let go, it simply wants to rotate about in a circle, following its own path. Okay? This time, so a non-spinning wheel falls down, but a spinning wheel stays upright. It's peculiar. But if it is ignoring the influence of gravity, then we should be able to measure it on a scale. And so over here, I have a second gyroscope.
Jim, I got it.
You got it? Thanks. I have a second gyroscope, which is fixed at 90 degrees on this board, and it can rotate about this pivot point here. And so when I tip it forward, it wants to tip forward. If I go out here, it wants to tip over this way. So, and in order to make it stop from tipping, I have to add a 100-gram counterweight. Now it's balanced. But let's see what happens when we do this demo when we spin it up. And now we let it go like the bicycle wheel. And we can see that if it goes forward, it doesn't tip. And when it goes all the way out, it also doesn't tip. And we can let that stay for a long time. In fact, I can even remove the weight that previously counterbalanced it. And you could say, Jim, you cheated, you pushed the board in. But what I can do is actually extend the board outward. I can even extend it further and further. So, let me give it a fresh spin so you can see it more accurately. So I can extend it out pretty far, about here, before it wants to tip back over. So if we stop it, though, at this position, and set it back at a fixed 90 degrees, I can then tip it back out and see how much overbalanced it became. So I can add the counterweight back, which isn't enough anymore. I can add more weight. Now we're at 300 grams. It's still not enough. I can do 500, and that's still not enough. I can go up to 700, slightly, add there, and we got it. So we went from 100 to 800. So it's about 700 grams overweight now, which is really interesting. Eric Lathwaite also claimed that spinning objects, the bigger they were, the better they performed. Need this. And so over here, I have an even heavier gyroscope attached to an even longer arm. So now, I'm going to try to hold it outright. Okay. So as it spins, it behaves just like the bicycle wheel and the gyroscope we saw on the scale. Except for this time, however, if I slow it down, it's all right. I can actually show you that I can't hold it out like I did previously when it's not spinning. Okay.
Oh,
thank you.
No, not yet. We're going to talk about. I already switched it.
So, what's going on here? If you believe your eyes, you can see that it lost weight. However, I can also tell you that all of these demonstrations are within Newton's laws. In fact, it's Newton's second law in rotational form that can describe how these demonstrations work. So with a bicycle wheel, like we had before, all it takes is a spinning mass on one axis and a rotational force on the other. And what you get is a precession on a third. And we understand how these work. In fact, we've actually engineered some really amazing applications with them. This example here is 2 gyroscopes. It's actually 2 40-pound gyroscopes spinning at 12,000 rotations per minute. And it's enough to stabilize this 2-wheeled motor vehicle. Even if it gets into a sideways impact, it can remain upright due to the conservation of angular momentum. And now, Eric Lathwaite understood all this, but it wasn't sufficient of enough of an answer, because he said no one could adequately explain how a 70-year-old man could lift 40 pounds over his head with one arm and couldn't do it any other way.
Kill the lights. Is helping people see effects that are ordinarily unseen. One of those effects has to do with the way light passes through different temperature air. And it's an effect that you know about whether or not we've brought it to your attention before. We all know the song, Twinkle, Twinkle, Little Star. Yeah. If you see the stars, it's on the left here, a highly magnified picture of the star is not round, doesn't look like a star. It blinks and, it's just ugly. The reason for that is that the light that comes from the star has to pass through the atmosphere, and up in the atmosphere there's some turbulent flows and some warm sections of air, some cooler sections, and the light gets passed through it and it takes a different path. Sometimes light misses your eye completely, sometimes it hits you directly in the center of your eyeball. And so it appears that the star is twinkling. Planets don't twinkle, the moon doesn't twinkle, but if you magnify the moon, you can also see this effect on craters. So we're looking at light passing through the atmosphere. It's called refraction. And this is due to turbulent airflows and temperature changes. Well, we can harness that down here in the room. So I've got a mirror, a light source, and a detector. Light from the light source is going to go down to the mirror, bounce off, and hit my camera. If you look at some other light, it goes to the same place. And right where they meet is a place called the focal point. If we take a knife edge, it's just a little razor blade, and place it right at the focal point, and then just consider one light ray, it just misses the knife edge. And if I put something warm between the mirror and the camera, the air currents will deflect the light little by little, some of it hitting the knife edge, some of it missing. So, you hold the camera for me? And so hopefully, this works really nice. All right, so you can see very clearly the bright spots and the dark spots of the light either hitting the camera or missing the camera, passing through the temperature difference. Okay. Even if the light's out, you can still see the air temperature, or the temperature differences. I also like the gas coming out of the lighter. So there it is lit. There's just the gas. We can do cold water. You can just barely see the air currents around it. It's not as exciting as the hot water. Well, it was hot. But if you get it tuned really well, this is where I'm hoping it's a good day. You can see the air coming off my hand. It's not perfect, but it's pretty darn good. Or just the breath. Okay. And I love taking effects that you see elsewhere and bringing them into the lecture hall. The first place this was discovered, or I guess observed, was by Robert Hooke at the Royal Society in London in 1665. It's been since updated. This was, blanking on his first name, Mr. Foucault in the 1800s. They also used this as a test for telescope mirrors. You can see how perfect the curve is. By moving the knife edge, you can see differences in the curve. It's a pretty good mirror. All right. Other applications of Schlieren imaging, what this is called, is looking at shock waves from airplanes. That's actually backlit with the sun, I believe. The NASA patent wasn't altogether amazing with its detail there. They wanted to sell it to you. Don't blame them. And then also high-speed images of bullets in flight. You can see the shock wave from the front edge and the turbulent airflow behind it. In this case, instead of looking at temperature differences, we're looking at air density differences. But it's the same effect. And the fact that we can do this in the room blows my mind.
All right, so Nick just got finished explaining to you a way to use air currents to visualize light changes, but he was primarily looking in the visible spectrum, the 400 to 700 nanometers within the electromagnetic spectrum. Our eyes are highly tuned to those specific frequencies. But as many of you know, there is wavelengths both shorter and longer than the visible spectrum. And one of the things that physicists do is try to utilize tools to help see these things that are at the different frequencies that may be radiating gamma rays, X-rays, or in the next case, infrared light. So I want to talk to you a little bit about that. So infrared light ranges just past the visible spectrum on the red end at 700 nanometers, and they can, and it's quite a long range, and it encompasses ones as large as 1 millimeter. And so it was first discovered in 1800 by William Herschel, and it was one of those things that is a happenstance kind of discovery, which happens a lot in physics. And what he did was have a prism come in between a incoming ray of the sun, which then broke that light up into the rainbow that a lot of you are familiar with. He then placed thermometers in each one of those color bands, as well as 3 thermometers that were outside of the color band as a control, because physicists like to make sure that what they're measuring is accurate. And so after he let the temperatures equalize, he found that there was indeed a temperature increase from the violet onto the red portion of the spectrum, but he also noticed that the one thermometer that was just outside of that color band also got hotter than the 2 other control thermometers. And this was indeed the first evidence of picking up signals that were beyond what we could readily see. And so one reason he was able to do that is if you take a look at the spectrum of the sun, you will see that only about 3% of the incoming radiation at the surface of Earth, it's different when you go above the atmosphere, but 3% of the light rays you receive from the sun is UV. About 44% of that is the visible that we are able to process, and then you'll see about 53% of the incoming radiation is actually infrared. And so we, again, as physicists, have built tools in order to be able to pick up these infrared radiation signals. And how do we do that? Well, we've built a camera. Basically, we have incoming infrared radiation. It strikes the surface of a lens. It's often a germanium lens because that responds a little bit better to the infrared spectrum. That lens then focuses the incoming rays onto a sensor that then is connected to a processor, which puts out a picture that we are all familiar with, just like on a digital camera. And so let me show you what you guys look like in the infrared. So we, as humans, actually radiate energy in the infrared spectrum, and it is, I must have unplugged the camera cable. There you guys are. All right. And so this camera is highly tuned to that frequency range beyond the 700 nanometer scale. And so you can see that we actually glow pretty hot. Another thing that I want to show you is that this device is able to pick up energy transfer awfully quickly as well. So you can see how cold my fingers are. But if I put my hand on the blackboard and walk away, you can see remnants of my handprint on that blackboard. And that only was a few seconds. And so you only need about a 4 millikelvin difference in order for this specific unit to be able to pick it up. But another thing that you guys might notice is that my eyes appear very, very blue, very cold. But if I remove my glasses, it's not that my eyes are very cold, it's that I'm actually wearing glasses which are an infrared filter. And so not everybody wears glasses, but everybody has experience with windows in their house. So if you, again, I showed you the spectrum of the sun. It has both UV, visible, and infrared. Well, glass in general allows most of the visible light, which is represented by the yellow line, through, which is why we choose it as a window. And you'll notice that a lot of the UV and infrared radiation is reflected. It is not able to transmit through that piece of glass, which is in the center of this picture. You'll see that it's not a perfect filter. There is some that still gets through, but overall it is able to block that infrared radiation. So I wanted to show you an experiment where we take advantage of this idea. And to begin with, I'm going to have a mirror on your guys' left side of the room. I'm going to place a light source at the focal point of that mirror. The light is going to hit that mirror and get collimated out across the bench. On the other side, I have placed a second mirror, and at the point where it focuses the light, I'm going to place an eyeball. Now, of course, I don't recommend you doing this. You don't want to look at the sun with your telescope because it's going to basically do this. But if you were to put a pair of sunglasses on your eyeball, you will see that it does not there's no issues. But if I don't wear sunglasses, you might be in for a little bit more pain. So let's go ahead and let's train your eyes over here. I realized I forgot a back plane, so I do apologize. But if you're not careful, don't ever look at the sun without the proper glasses. All right. So there are many uses for infrared radiation, or for detecting infrared light. One of those is used in the military to both find humans as well as munitions that may be under the ground, so that is a couple landmines that they can detect. It's also used in hunting and environmental conservation to locate animals in the wild. It is used in inspection, so if you ever are wondering if you're leaking water or if you have an electrical issue, infrared radiation can help you with that. It's also used in medical applications. So the blood is warm, and you can use an infrared camera to actually see how the blood flow is within your body to help those that may have diabetic retina or diabetic foot issues and things like that. And my favorite application of all is astronomy. When you start looking at things like Jupiter or Andromeda on the right, or the Orion Nebula, which looks vastly different in the infrared spectrum than it does in the visible spectrum, you really get to start putting the full picture together of what's happening in places that we might not necessarily be able to touch. All right, so another place that we can use infrared radiation is to kind of keep track of energy transfer. So if I take a ball and I drop it, we've had a lot of transfer of energy from where it starts to where it ends. So initially, it has some potential, because it's off the ground, it has the potential to do something. If I let it go, it has motion, so the energy of motion. When it strikes the ground, there is a quick change of energy at that point, and it transforms into motion back, so we know we haven't lost all the motion, but we also, so it transfers into, potential kinetic. There may be some rotation, because I didn't drop it perfectly straight. What other kind of energy might it transform into? Well, we heard it hit the ground, so we know that there's sound. And then one that may not be so obvious is heat. And if you don't believe me that this heats up, have any of you seen the slow motion drop of a golf ball? See how much that deforms. That is, this is at much higher speeds than what I'm doing, but still on my scale, this is happening. I would just have to drop the ball about 50 times for you to actually see the heat. And the other problem is that I'm holding it, so I've also got that transfer from my hand. But if we use that idea of deformation, we can then show you the infrared release of energy due to deformation. So I'm not going to deform a ball, but I'm going to use our favorite prop, and that is a soda can, or in this case, an Ale 8 can. I'm going to give this block a whole lot of potential energy. Got to go to the top. And then I'm going to let it go. And in that instant, you're going to be able to see the transfer of energy. Whoop, it got caught. Hold on. That was not as spectacular. Try that again. 3, 2, 1. All right. So I've definitely crushed the can. And sure enough, it is hotter than it was when it started. Okay. So, let me get the screen back. So not everything that we do needs to happen quickly. There are other ways to transform energy and help dissipate it in ways that are useful and applicable to our life. One of those is through magnetic braking. And so magnetic braking is where we use magnets to help slow down a conductor that can be influenced by that magnetic field. And some of those applications are in bullet trains and brakes for any kind of large rotating machine. Roller coasters use eddy current braking, as well as your elliptical machine. For those of you who know, you change resistances. All it is changing the position of these magnets around a spinning disc to slow it down. And again, on the idea of visualizing this transfer of energy, we have another demonstration of exactly this braking. And so Jim is going to be performing this, but basically we are going to have a spinning disc, and he's going to place a horseshoe magnet, which is very strong between the poles, around that spinning disc. And if you've watched the picture, you'll be able to see what happens as a result. So clearly you can see that magnetic energy being transformed into heat as the disc begins to slow down. All right.
Okay, so what we just saw with the infrared camera was that a magnet induces a current inside the material, which then turns it into heat and light. But you also saw that the rotor slowed down. And now this is actually a bit of a two-step process of where ultimately the energy goes. The magnet has to induce a current, which is what is actually dragging the rotor. It's not the resistance. The resistance only turns the current into heat. So resistance is a material property, and the best way I can describe it is like running through the woods blindfolded. You're probably going to hit a tree. Versus, say, running on a football field, there's nothing to impede your motion. And so it would follow that if this material had less resistance, that the rotor would actually slow down faster. And so there are materials that have zero resistance, and so an induced current would actually last forever. Oh, sorry. And we call this superconductivity. And so a superconductor is kind of like water. It's that water is kind of like water because water turns into ice at 32 degrees Fahrenheit, whereas superconductor, which is normally insulating at room temperature, turns into a perfect conductor of electricity at negative 294 degrees Fahrenheit. For comparison to how cold that is, the coldest recorded temperature on Earth ever was in 1983 in Antarctica, which was a negative 128 degrees Fahrenheit. And so even though superconductors are difficult to understand what's going on inside them, they're actually relatively easy to make. If you're familiar with baking, they share a similar recipe to that of pie dough. A pie dough is 3 parts flour, 2 parts butter to 1 part water, where a superconductor is 3 parts copper, 2 parts barium, and 1 part yttrium, which are elements of the periodic table. And so in order to test for superconductivity, we have to test for what's called the Meissner effect, which is the expulsion of all magnetic fields. And so what happens is that the magnet actually induces currents on the surface of the superconductor, which behaves as a magnetic mirror. And so even though the magnet is on top of the surface, once it cools down below its critical temperature, it will actually begin to levitate. And let me demonstrate that. So lucky for us, I actually have a bucket full of negative 290 degrees Fahrenheit beverage, which I can add to this demonstration. Okay, so I'm cooling it down. I'm also going to get the second one prepared, because it takes a little bit longer. Okay. Woo. So what's really neat is that the Meissner effect expels all magnetic fields, and it doesn't care about the orientation. And so as it cools down, you'll actually see that it levitates up. So it might take a little bit. It has to get really cold. So what's really neat is that the currents are actually strongest at the surface, and the currents actually gradually decrease going inward. And so the magnetic fields can actually only penetrate the surface about a few millionths of a meter to a few billionths of a meter. And so that actually gave scientists a crazy idea. It's taking longer than I expected. Come on. Close. Close. There it is. Wonderful. And so this is the expulsion of all magnetic field. It's like a magnetic bearing. It's actually spinning really fast. I don't think the camera can see it. It will slow down. Okay, and so the fact that the magnetic field can't penetrate the surface because it's such a perfect conductor, it's a magnetic mirror. And so that gave scientists a crazy idea. They said, what if we engineer defects into the material to trap it in order to trap it after it cools down, instead of expelling it? And that is called magnetic field trapping, and that is our second demo. So let me just switch this out carefully and slide this one in. And so I have the setup that's on the screen on the left. It's a superconductor disk, a large magnet, and a spacer. And so magnetic trapping only cares about the field strength of the magnet, which means we can actually set its height using a spacer before we trap it. And you can imagine how useful that would be for engineering applications. I can literally set the height of where I want my superconductor. And so what happens is that since the currents are strong at the surface, by adding defects, which is kind of like driving on a road here in Michigan with a bunch of potholes, or you can imagine as the cookies in a chocolate chip cookies. The defects can be added through sources of radiation damage or by using non-superconducting inclusions. The end goal is to allow greater magnetic penetration into the superconductor, and by doing that, it also helps trap the field in place. And so I've done the demo on the left here, but I'm going to show you what happens when I remove the spacer. And you can see that the superconductor has locked it in place. And it can even spin freely, because at that height, the magnetic field is the same field strength. What it doesn't like is being pushed up or being pulled down. And if it's strong enough, I can actually hold it sideways. Okay? In fact, in order to show that I'm not using any strings, I'm going to put it through this tube here. My space isn't big enough. I tried. But you can see I can stick the whole thing in. How about that? Okay, and then now the last thing I want to show you is that I can, to prove that there's currents inside the superconductor, even when there's no magnetic field, I can remove the magnet and then hold the superconductor up near these compasses, and I can show you that it deflects, just like a magnet would. And so that's evidence that there's perpetual currents in there because of the state of zero resistance. Okay? And now over here, to demonstrate further that the magnetic field trapping only cares about the field strength, I have this magnetic track. So it's a big elliptical track, and the magnets go north on the outside and south on the inside. And so we've designed a track that changes the field strength in an orientation that we desire. And so what that does is it allows the superconductor to stay on track and not fall off while it goes around. And so instead of using a large puck sample, we actually have a highly engineered thin film superconductor. So this thin film superconductor is actually only a few millionths of a meter thick. And so let me cool it down. And so it's only a few meters thick, which when I cool it down, actually, could you give me the tweezers? Thanks. Let it cool down slowly. Thank you. Okay. And once it comes to temperature, I can place it on the track. Let's see. So it's actually relatively easy to place on the track compared to the other ones because of how thin it is. And so it's easy to set in place. I can actually pick it up, change its orientation. I can twist it. I can dip it over. It doesn't mind because it's so thin that the magnetic field is easily penetrating it. And so unlike the other ones, this one doesn't have any defects. This is actually purely currents that are holding it in place. If it was thicker, say about 3 millimeters, I couldn't do this because it would actually take the weight of a car to position it. And so it's so strong and easy to levitate Let me cool it back down. Like before, we can actually suspend it upside down. Oop, that's loosening it. Okay. So now we have an upside down track. I'm going to repeat the same thing. Stick it on, and I can just push it around. And so you can imagine that maybe someday this will be the future of our transportation systems. Yeah, it warms up quickly. Thank you.
All right, so Jim showed you a lot about permanent magnets, but another thing that physicists can do is create electromagnets. So if you send current through a wire, that current produces a magnetic field that is in a circular pattern around that wire, just like in the picture here. If I then take that wire and wrap it around into a coil, all of those little magnetic fields add up and become a larger magnetic field. And if you look at the magnetic field around this solenoid and compare it to a regular bar magnet, they look basically the same. So let's see what kind of advantages we can take with this creation of an electromagnet, because it's a lot more difficult to carry around permanent magnets. It's a lot easier to put electromagnets in almost anything so that it's only on when you want it. And so let's go back one. All right, so this demonstration is very simple. All I have is a momentary contact switch, so it just lets me turn it on when I want. And then here is just a coil of wire, okay? If I place a conductor within that magnetic field, I'm able to induce a current in that material, just like as if I were to apply a direct voltage. I can use that magnetic field to do the opposite. So it's experiencing that magnetic field, which then in turn creates a current around the wire, or in this case, a solid ring. If I place that ring into my solenoid and turn it on, you will indeed see this reaction, okay? Not very impressive, but you can see it. If I then place a core, a conducting core, so in this case, these are actually just hangers that have been sliced off, so not even a really specialized conductor. But if we place that inside of our field that we have created, we can then amplify the effect. So if I repeat this, so that's one way that we can utilize this. We can also use it to create power, a current to produce, anyways. So, sorry. If I go ahead and put current through our solenoid, I then just have a loop of wire that has a bulb on the end of it. And I'll be able to show you the current that's actually produced. With one loop, not really much. If I do a few more loops of wire, you then can actually start to see the light up. And if you then continue to wrap wires around, in this case 200, you, instead of lighting a little flashlight light bulb, you can actually light a 100-watt light bulb. Okay? And as you can see, I had to go fairly close to where the current was generated, because the further you are away, the magnetic field falls off, like 1 over the distance squared. And so that does matter. But we can do some really neat things with it. So Jim had mentioned that there was resistance in the system, and that resistance can transform into heat, like you saw in the eddy current braking, or the magnetic braking. We can do the same thing here. So you saw about how high this solid ring went. It's not exactly the same one, but that's okay. So this one wasn't as thick. But you do remember what happened with the last one. If I then go ahead and chill it down, I am effectively reducing the resistance within the ring. And once it chills down enough, I meant to have this pre-prepared, but I did not. And I repeat the experiment. You can see that it can go much further without that resistance. So another application of this effect is seen in when you're trying to machine an object that may not be easily cut out with a mill or a lathe. You can also use magnetic fields if it's a thin enough piece of metal that you're trying to form. So in this case, we have a workpiece which is just a cylinder. We have a non-conducting die. You place those two objects inside of a coil. You send current through that coil. It produces a magnetic field. And in this orientation, just happens to push in towards the center of this ring. And it then forces this metal, to then form to the shape of that die. Another application of it is also in electromagnetic welding. And so this is in the case where you have a conducting material and a non-conducting material. You can't readily weld that with a TIG welder or a MIG welder because it's dissimilar materials. But if your outer piece is magnetic, you can do the same thing. Your center piece, which has this weird lip on it, gets set in the center. You put the thinner piece that you want to form around it. You apply that magnetic field, and it forces everything in. So let me show you an example of that. This is a demonstration known as our killer capacitor, because it has almost killed a couple professors. But we have hopefully insulated it so that we don't do that anymore. But the name is legacy and helps remind professors to be careful when they're using this apparatus. But it essentially consists of a capacitor bank of 3 large capacitors. There's only about 7 millifarads a piece, but when you apply the voltage of 10.5 kilovolts, you get a hefty output. We are then going to discharge these capacitors, and I'm going to go ahead and start the charging now because it takes a moment. But we are going to discharge these capacitors through a coil, which is sandwiched in between this plastic here, but it's basically 4 turns and goes directly back to the circuit. So there's nothing funny inside of here, just 4 turns of a coil of wire. Once I charge this up to 10.5 kilovolts, I am then going to close the switch. The capacitors are going to drain very quickly through this coil, and you're going to actually see the effects of the magnetic field produced. Now, I did this ahead of time, but there's basically a pop can that is sandwiched halfway between the coil. So half of it's above and half of it's below. And it's going to be loud, so I'm going to give you a countdown. And when I do, please plug your ears. Don't cover them like this, but actually plug them. All right, you guys ready? Here we go in 3, 2, 1. So what you saw produced is actually the vaporization of both sugar as well as the aluminum can itself. And so those magnetic fields were able to force it into the center, and actually, since there's a force going up and down, it actually ripped the can in half. So in this case, the piece itself is too heavy for it to move, but in the case of a light can, you actually saw the movement. Now my last question to you, it's a silly one. Why are these different? So there's nothing really different about it, right? Just 2 sides of a can. Well, the difference is when this quickly contracted, all of that air inside there got heated up and wanted to expand. Well, in this version, there was nowhere for it to go, so it actually came out the same way that it went in and spread it back out. Versus this side, you'll see there's actually somewhere for that air to go. And so you can actually see that the forming stayed in place. Okay, so this next demonstration I have for you is just a really cool one, so I'm not going to go into a lot of detail. I do have some information on it if you guys are curious. But this next demonstration uses the same idea of applying a magnetic field to a set of coils, which produces that magnetic field in the center, just like in that picture there. And we are going to use that to accelerate a solid 3/4 inch aluminum or a steel rod down our tube, okay? Now, what makes this interesting is called a linear accelerator, and so Jim kind of mentioned a little bit about the linear induction motor. This works in a similar way, but rather than having the object on the outside, we're actually propelling the object through the center of this tube. The other thing that I want to point out is you notice that the size of the coil is increasing as you go from right to left. And if you think about the speed of that projectile as it's traveling down our tube, it's going to get faster and faster and faster, so that acceleration is always increasing. Well, we want to make sure we're increasing it linearly, and the only way to do that is to make sure we account for the distance that rod has traveled so that we pulse it at the right time to continue moving it forward. And so to do that, this one's a little noisy, but we have connected this to a 3-phase power supply, and all that means is we're going to fire every 3 at the same time, or every third one at the same time. But it doesn't matter that the same coils are being engaged because the projectile has moved on from that. But what's important is, again, is this timing in order to get this to accelerate. Now this one is also a little loud, and so where did I grab my muffies? So I'll give you guys a countdown, and you're going to want to cover your ears as well. So, turn on the power, start the switch, and here we go in 3, 2, 1. And it pops itself back in, but there you go. And so I just wanted to remind you guys of the electromagnetic pulses in the wire. It's kicked at the right time, and then the coils are there to help keep it a linear acceleration as it goes. All right.
We don't always have to have electricity to have a lot of fun around here. I mean, it's nice, but we don't need it. In fact, historically, Galileo, when he was under house arrest, was doing studies on projectiles using a ramp, a table, and some brass balls with ink on them. So what he would do is he'd roll a ball down the ramp, hits the table. Aw, animation's not working. Goes flying off and strikes the ground. When it hits the ground, it leaves a little dot. And by measuring the distance it traveled and the height it dropped, he could work out that projectiles follow parabolic trajectories. And here's hoping this works. So I'm going to show you one of those trajectories. Now, unfortunately, it didn't quite follow that path. It was close. But it diverges a bit at the end. Because in a perfect world, there's no air in the way. Yeah. So, we have to account for that. It's a lot more noticeable with things like a ping pong ball. So if I throw this, it slows down pretty quick. So I actually took a video of Jim doing this. Was it Wednesday?
Something.
This is a cell phone video. I took it into a free program called Tracker. You can plot the position of the ball, export that data to an Excel sheet, and then plot the actual path. Okay. By the way, if you want to do this at home, it's free. Okay. And the tutorials are amazing. If you plot the actual path it should have taken, you can see it diverges pretty rapidly. So if you want to model the air resistance, you have to know how fast the ball goes if it just falls forever. Okay, so we need to find the terminal velocity of that ball. And I did it this way. Figure the ball's constantly falling. All you have to do is measure how fast the air goes here. So that's the easy way. The hard way is you have to know exactly how the surface interacts with air, exactly how much air pressure there is in front of the ball, the exact speeds. But once you know the terminal velocity, you can work out a pretty good approximation. There's two main ways to model drag. One of them is linear. That's not that great of a model for my ping pong ball. Another one depends on the speed of the ball squared, and that's a much better fit. Real resistance isn't quite right there, and I was pretty haphazard on my terminal velocity measurement. So considering that agrees that well, I'm pretty happy with that. But that makes me wonder how fast we could actually move a ping pong ball. Now, I can't throw that fast. I'm not a pitcher. I don't have those skills. After that. Nope. Make sure I'm not skipping anything. But what I do have is a lot of time and pneumatics. So, I figured I'd give this a shot. And I kind of hate pop cans. So we're thinking, we'll wait for Jim to get out of the range. So I'm wondering how fast this actually goes. Here we go, 3, 2, 1. Feels kind of dangerous, doesn't it? I wonder just how dangerous this is. Love doing good science. Anything? Oh, just a dent. Okay, so I really want to do more damage than that. I mean, she got to rip a can in half already. So despite having the little air cannon, I'm still limited by the air in front of the ball. I can't push the ball any faster because there's stuff in front of it. So all we have to do is get the air out of the way. So this is our vacuum cannon. What we've got is one end sealed with freezer paper. We're going to put a ball inside, seal off the back end. Then we're going to take a vacuum pump and suck all the air out of it. Once we get down to pressure, once we get down to minimal pressure, we're going to open the end, let the air pressure around it push the ball forward. Now, I was using 80 psi in my little rifle here. That's only about 15 psi with the atmosphere. Now, we're limited by a couple things. One is how fast the air can actually rush in. The other is the residual air in the tube getting compressed at the end. But we've worked out it's going to be just under the speed of sound, about 280 meters per second. Fired basically point blank into a pop can. This one's also going to be loud, so please, when she gives you the countdown, plug your ears.
You guys ready? Here we go. 3, 2, 1. Oh no!
Significantly more damage. I was hoping for a hole clean through it.
Usually
but
is.
sometimes it doesn't work that way. We did bash the heck out of the ball though. So I'll settle for that.
So we want to thank you, all you guys for coming out. We want to do a special thanks to the physics department for hiring us all. For Fred and Myron and Tim and Carol for making this the wonderful program that it is. As well as the lesser known people who help keep this place going, like Marianne, Karen, and Aaron, who help with the food, as well as Michigan Productions, who help us keep track and record all of our lovely fun that we have here. And of course, Warren Smith, because without him, I don't think the Demo Lab would be what it is today. So.